Let's suppose you encounter this kind of problem on the SAT subject physics test. You have a car of mass m which makes a turn of radius r while going at a speed of v miles per hour, and it does this while managing not to skid on the surface. Then the mass is doubled and you are asked to find the velocity necessary to do this exact same movement. And so here I've drawn the circular corner and its center and the radius and the velocity of the car of mass m. Now let's just find out what forces are actually acting upon the car. Now, since the car is in a circular motion, we have the centrifugal force acting upon the car, trying to push it outwards. And so I'm going to denote the centrifugal force F sub 1. So we know from our theory that the module of F sub 1 is m times the velocity squared, that's the speed actually, squared, divided by the radius of the corner, which is just the radius of the circular trajectory. Now, the other force acting upon the body is the friction force between the car's tires and the road, which tries to pull the car inwards, thus keeping it on the road. And so I'm going to denote this force F sub 2. And the value of F sub 2 is, again from our theory, is the friction coefficient mu times the car's weight, which is just m times g. And so now we have the expressions for these two forces, and we are going to find a formula which relates them to one another. And so we are going to go back to the rubric and just highlight this bit here. Now the phrase without skidding means that the car is in dynamic equilibrium. In other words, the resultant force acting in this direction here is 0, and so r is a vector and is equal to 0 because the car does not skid. And so r, we also know that r is the sum of these two vectors that we've just talked about, f sub 1 plus f sub 2. And we also know that the vectors f sub 1 and f sub 2 are on the same line. And again, this is from theory. And so from here, we can deduce that the sum of these two vectors is 0. And then, considering the fact that they are on the same line, we deduce that their modules are actually equal, and so I'm going to write the module of f sub 1 equals the module of f sub 2. And so if these are the values of these two forces right here, we can just write m times v squared divided by r equals the friction coefficient times m times g. And so we quickly see that the mass of the car cancels, and so we are left with v squared divided by the radius of the circle equals mu times g. And so v is square root of r times mu times g. And now what I'm going to do is that I'm going to put this formula in a box because it's very important. If you look carefully, you will see that there is no mass going inside this equation, which means that the velocity, the speed actually, does not depend on the mass. I'm just going to write it here. V does not depend on m, on the mass of the car, which means that v is not a function of mass. So the speed of the car while doing this kind of motion is not a function of the mass of the car, and so it does not matter how the mass of the car is modified, i.e. doubled, because the velocity will just remain the same as in the initial case. And so the answer to the question is that the velocity, the speed actually, v, just the speed required, is v, is the exact same speed as in the initial case, because the velocity, the speed is not a function of mass. Okay? Yeah, so that is it. Just so that I'm going to put here a recap just so that we have it here. V with the vector, this is velocity, and this thing is equal to v. This is the module of the velocity. It's the speed. It's actually the speed. Okay, just to be clear. Okay, so that's it. That's how you solve this problem.